Welcome back to this module on pipelining. The topic of this lesson is structural hazards and data hazards. First, a quick recap of the previous lesson. In it, we saw the canonical 5-stage pipeline consisting of the stages instruction fetch, instruction decode, execute, memory access, and write back. We also saw that the MIPS ISA was specifically designed to support this pipeline, but we also saw that there are some hurdles that need to be taken. The pipeline hazards. A hazard is a situation that prevents the next instruction from executing in the next cycle. There are 3 kinds of hazards: structural hazards, data hazards, and control hazards. In this lesson, we will study them in more detail and discuss potential solutions to them. First, structural hazards. Structural hazards occur when the hardware resources cannot support parallel execution of instructions. Here's an example to make it clear. There are no structural hazards in the pipeline organization as we have discussed until now, but we can easily introduce them. Suppose there is only one memory with a single port that is used for both reading and writing. To illustrate the hazard, we draw again a pipeline diagram. As usual, time is displayed horizontally and divided into clock cycles, and the instructions are shown vertically from top to bottom. The first instruction is a load, and instructions 2, 3, and 4 are arbitrary instructions. The load will execute like this. In the first cycle it is fetched, in the second it is decoded, in the third its effective address is calculated by the ALU, in the fourth cycle the data is loaded from memory, and in the fifth it is written back to memory. Similarly, the second instruction will execute like this, and the third instruction will execute like this, and the fourth instruction will be scheduled like this. Now we observe that in cycle 4, the load instruction accesses memory, but in the same cycle, memory is also accessed to fetch instruction 4. Because, as I assumed, there is only one memory with a single read-write port, the hardware cannot support this. To solve this hazard, the execution of instruction 4 has to be delayed by one cycle, like this. Now I will discuss data hazards. Before I do so, however, I first need to define exactly when the register file access takes place. You might have noticed that in our pipeline diagrams, in the instruction decode stage, when the register file is read, the right side of the register file is colored blue. While in the write back stage, when the register file is written, the left side of the register file is colored blue. This was not done by accident or because it looked nice. No, it was done to emphasize that the register file read takes place in the second half of the clock cycle, and the register file write takes place in the first half of the clock cycle. So if instruction I reads a register that instruction J writes in the same clock cycle, then instruction I will read the value written by instruction J. Note that this is just an assumption. It's not an unreasonable assumption because a register file access usually takes less time than a memory access and even a cache access. But other organizations with different timing properties are possible. A data hazard means that an instruction depends on the result of a prior instruction that is still in the pipeline. To illustrate this, let's again draw a pipelining diagram, and as usual, time goes from left to right and instructions go from top to bottom. The first instruction to execute is this add instruction that writes to register R1. The second instruction is a subtract operation that reads from R1. The third is an AND instruction that also reads from R1. And finally, the fourth is an OR that also uses R1. The add instruction executes like this, and the subtract instruction is scheduled like this. Now we see there is a problem. The add writes back its result to R1 during the 5th clock cycle, during its write back stage, but the subtract instruction reads R1 during its instruction decode stage in the 3rd clock cycle. This means that the subtract will read the wrong value, an old value of R1. Similarly, this AND instruction will also read the wrong value for R1, since it reads the register file in clock cycle 4, but R1 is only written in clock cycle 5. This OR instruction, on the other hand, will read the correct value, because we assume that the register file write takes place in the first half of the clock cycle, while the register file read takes place in the second half of the clock cycle. Clearly, we have a problem that needs to be solved. How do we solve it? Should we stall the pipeline for 2 cycles so that the subtract and AND instruction will read the correct value? No, such dependencies happen way too often. This would make our processor way too slow. Then what? An often used solution for data hazards is called forwarding or bypassing. It means that we do not wait for the result to be written back to the register file before using it, but instead we use it immediately by forwarding the result from one pipeline stage to the next. To explain how it works, let's consider the same example as before. At the end of the 3rd clock cycle, the result of the add operation is available in this pipeline register. In the 4th clock cycle, the result is needed as input to the ALU, as indicated by coloring the ALU red. So instead of waiting for the result to be written back to the register file, we add some data paths so that the result can be immediately forwarded from the XMEM pipeline register to the first input of the ALU, as indicated by this green arrow here. Similarly, the result of the add operation is again needed by the ALU in clock cycle 5. Now the result is available in this pipeline register, the MEM write back register. So we should add some data path so that this result can be forwarded from the MEM write back pipeline register to the ALU, also as indicated by the green arrow here. Finally, the OR instruction also needs the result of the add operation, but now it's already available in the register file in R1 as indicated by this green arrow. So we see that some extra hardware can be used to eliminate most data hazards. What hardware changes are needed for forwarding? This figure shows part of the pipeline data path that we developed in the previous lesson. First, we need to expand the multiplexers in front of the ALU inputs. Larger muxes are needed in order to be able to select between the data that was read from the register file in the previous clock cycle and the result available in the XMEM or MEM write back pipeline registers as indicated by these blue wires. This forwarding unit here controls these muxes. What function does the forwarding unit perform? It checks if the destination register of the instruction currently in the MEM stage, or equivalently currently in the XMEM pipeline register, or the instruction currently in the write back stage in the MEM write back pipeline register, is equal to one of the source registers of the instruction currently in the X stage, in the ID X pipeline register. If this is the case, then the forwarding unit steers the multiplexers to select the correct input operand. This figure is a stylized drawing, leaving out several details such as handling the case of an instruction with only one input operand. These details can be left as an exercise, but be aware the devil is in the details.